one of our local NBI or NBIA people. So Shashank is an assistant professor who's working on neutrino interactions in dense astrophysical objects, and you will talk about effects that this has on flavor conversion. So please.
Okay. So first and foremost, I want to thank Marcus and Mauricio for inviting me to give a talk. Okay, so what I'm going to do is, since this is neutrino school, I don't want to assume too much regarding core collapse supernovae. So I'm going to give you a brief introduction about what core collapse supernovae are, the role of neutrinos in core collapse supernovae. Then I will discuss briefly neutrino transport. Then I'll shift gears a bit, and we will discuss a bit of neutrino flavor evolution, and then come back to core collapse supernovae and discuss what role do these neutrino flavor evolution can have on supernovae. Okay. So what are supernovae? Supernovae are violent depths of stars which are more than 8 times the mass of the sun. Okay? So if you look at the picture here, you will see an example of a supernova that happened quite nearby us in the Large Magellanic Cloud. So this arrow is pointing at a small star which was photographed right before it went supernova. That, as you can see, it's a very faint object. But after it went supernova, it became really bright. And the supernova can be brighter than the host galaxy. So basically, when a star goes supernova, it becomes brighter than the galaxy it resides in. So huge amounts of energies are released. So why does this supernova happen? In order to understand that, let us go back to the last stages of the life of a star. So we all know that stars release energy by nuclear fusion. It starts by converting hydrogen to helium. And at some point, the hydrogen in the core is exhausted. Then what happens is that the temperature increases in the core. Helium starts getting converted to carbon, so on and so forth. The chain continues. Heavier and heavier elements are produced until at the center we form a core made up of iron group elements, so iron, nickel, etc. And when this stage is reached, no more nuclear fusion is possible because the iron group elements are the most stable elements in the periodic table in terms of the binding energy per nucleon. So if you try to fuse iron group elements into heavier elements, you have to supply energy. It does not release energy. You'll have to supply energy. So it is not feasible for heavier elements to be formed in stars. And the result is that the iron core, which was there, it becomes unstable because there is nothing to stop the gravitational collapse of this core. And the core starts collapsing. So here is a schematic view of how this core collapse happens. The inner core undergoes a homologous collapse. What that means is that if we look at the velocity, this is the velocity. If we look at the infall velocity, then the infall velocity is proportional to radius. The whole object is shrinking as a one object. It's just shrinking. And as time goes by, the velocity of the infall obviously increases. So the velocity keeps on increasing. But velocity is proportional to the radius. This can't continue forever because at some point, the infall velocity would exceed the speed of sound. And that is not possible. The communication is not possible faster than that. So the outer regions are not falling that fast. Okay, so the linear relationship has to break at some point when the velocity reaches the speed of sound. Okay, so the inner core continues to collapse until it reaches nuclear densities. When it reaches nuclear densities, the infall of the inner core stops and the outer core slams onto the inner core. The result is that what happens when an object hits a very heavy object? It bounces back. And that is exactly what happens here. The outer core hits the inner core and bounces back. Now here we have the bounced material going out with positive velocity, while the outside material is falling in with a negative velocity, negative radial velocity. The result is a discontinuity in this velocity, okay, as you can see. So part of it is going outward with positive velocity. Rest of the matter is falling in with negative velocity with a discontinuity in between. And this discontinuity has a name in fluid dynamics. It's called a shock. And this shock wave continues going outward. And as it moves outward, it destroys everything in its path. As the shock wave passes through the outer parts of the core, it will destroy the iron nuclei. It will break up the iron nuclei and convert it into alpha particles. And in the process, the shock wave loses energy, because if it is doing work, breaking up these iron nuclei, the shock has to gain that energy to do that for somewhere. And it basically is losing energy in doing that. And at some point, the shock loses so much energy that it stalls. It is not moving forward anymore. So if the shock does not move forward, how will the supernova explosion happen? For this, neutrinos come to the rescue, because at some point, neutrinos start depositing energy into the region of the shock, leading to hydrodynamical instabilities, and that revives the shock. And that is why we are interested in the neutrinos. So neutrinos play actually two roles. First and foremost, as I was mentioning, they deposit energy near the shock region and cause the shock revival. But they also play an important role as far as the cooling of the protoneutron star is concerned. Because notice something happened, right? When we started with a big star, the gravitational collapse happened. The gravitational potential energy, which is negative, decreased by a lot. So where did that energy go? Energy has to be conserved. So that the rest of the energy is emitted in the form of neutrinos, because no other option is possible. Nothing else can carry energy out of that dense region. Neutrinos are the only particles which are so weakly interacting that they can carry energy away from that dense region. So you have this situation where you have this cooling region in the deep interior, and the outside part, the neutrinos are responsible for heating. Okay. So as far as the energy budget of the supernova is concerned, neutrinos play a very important role. In fact, 99% of the energy released by a supernova is in the form of neutrinos. And the neutrinos play an important role as far as heating and cooling processes are concerned. But the processes involved in the cooling and heating are not exactly the same. As far as the cooling rates are concerned, there is contribution from beta reactions as well as thermal processes like pair production and Bremsstrahlung. But when it comes to the heating rate, it is primarily done through beta reactions, okay? And we will see why that is important later on, okay? So how do we, now that we know, okay, neutrinos are playing an important role, how did we find that out? How do we do calculations regarding this matter when it comes to an actual supernova simulation? How do we do this calculation? We do that using something called a Boltzmann equation. This equation basically tells you where the neutrinos are, where they will cause heating, where they will cause cooling. these terms, C absorb, C emit, and C scatter, they are telling you about the reaction rates. These are the inputs of this equation. And what we want to find out is F. And that is the number density as a function of momentum and spatial coordinates. And we want to evolve it as a function of time. Now, this is a 6+1 dimensional problem. 3 momentum coordinates, 3 spatial coordinates, 1 time coordinate. So it's an extremely difficult problem to solve. In fact, we cannot solve it. It's so computationally expensive. Okay. Okay. The figure is gone.
But this is a PDF, right?
Yeah. Should we switch?
We can. Yes, let's. For this one figure, let's switch, and then let's switch back. Yeah.
Okay. Are the other figures there?
You continue.
Okay.
And I will put this
Okay. Okay. So here is the solution of the Boltzmann equation. But I have done this assuming spherical symmetry. So that 7-dimensional equation we had, that becomes much easier to solve when we have spherical symmetry, because then, because then the number of dimensions has reduced, and it is possible to solve. And when we solve the Boltzmann equation, what we find is that if you look at, if you look at the x-axis, that is the angle with respect to the radial direction. So, and you have a isotropic distribution of neutrinos. What that means is the number of neutrinos going in the radially outward direction is essentially the same as the number of neutrinos going radially inward. The neutrinos are isotropically distributed. That means they're trapped. They are not able to escape. They're just moving around in circles in this dense region. But as we go to larger radius, what happens is that neutrinos start escaping. There are more neutrinos going in radially outward direction and virtually none going radially inward. So these kind of solutions tell us where neutrinos deposit energy and where they cool matter. Okay.
Yeah, you can just continue on the screen, and I will synchronize here.
Yeah. So one more thing is that the Boltzmann solution for these energy neutrino transport, that is a flavor dependent thing. You can see here the energy spectrum of the various flavors of neutrinos. The nu X represents heavy lepton neutrinos. These are muon neutrinos, tau neutrinos, and their anti-neutrino counterparts. And they have a high energy tail. Why? Because these heavy lepton neutrinos don't undergo beta reactions. So they decouple at a smaller radius where the temperature is high. And that is why they, on an average, have a higher energy. And electron neutrinos, they have the highest interaction rate. So they decouple at larger radius where the temperature is low, and that is why they have a lower energy. Okay? And the heating rate due to neutrinos goes like the cube of the energy, because the cross section goes like E squared, and each neutrino will deposit amount of energy E when it comes to the heating. So the heating due to neutrinos goes like E cube. And as you can see, that since only the nu E and nu E bar cause heating, they are not very efficient because they don't have this high energy tail. Okay? But what if some of these new X, these heavy lepton neutrinos, converted to nu E. Then they will help with the heating. And that is where neutrino flavor transformation or neutrino flavor evolution comes in. Because we know that the neutrino flavor is not conserved. Neutrinos emitted as one flavor can get converted to neutrinos of other flavor. So let me just clarify the terminology. Neutrino flavor evolution, by that I just mean neutrino oscillations, but oscillations typically imply oscillatory behavior. And here we don't have oscillatory behavior. That is, I'm using the term neutrino flavor evolution. And the evolution is essentially governed by Schrodinger equation. So we have a Schrodinger equation which tells you how the flavor of the neutrino evolves as a function of time or as they propagate. Here I'm giving a simple two-flavor approximation for the Schrodinger equation that governs the flavor evolution. Now, in vacuum, this Hamiltonian has a very simple form. But when neutrinos travel through medium, this oscillation probability changes. Because as the neutrinos travel through material, like a bunch of electrons, they scatter. And each electron, which is responsible for scattering, will emit a scattered neutrino wavefront. This leads to a constructive interference in the forward direction. This phenomena is generally called refraction. And that is what happens in the case of neutrinos. But in the case of neutrinos, the refraction is slightly different than the one in the light because there are multiple flavors. And each flavor is undergoing different amount of refraction. The result is that when neutrinos travel through material, its oscillation probability or the flavor transformation probability is different from that in the vacuum. And I'm sure you have learned about this in the lectures. Maybe if not, you will learn soon. But there are another kind of medium effect that usually is not discussed. And that is the refraction experienced by neutrinos because they pass through a medium of other neutrinos. This is called neutrino self-interaction. So neutrinos will experience refraction because they pass through a gas of other neutrinos. The Hamiltonian for such a phenomenon is a bit more complicated than what we saw earlier, but you don't need to understand what's going on here. The only thing you need to notice is that the Hamiltonian H depends on the state of the neutrinos. Okay, so what that means is that the Schrodinger equation, which governs the neutrino flavor evolution, is now nonlinear. And when nonlinearity comes into equations, weird stuff happens. One of the weird stuff that happens is that when we evolve the neutrino flavor evolves in a way that neutrinos of different momentum modes evolve in a correlated manner. And that is why the term collective is used to describe this phenomenon. And the time scales associated with this flavor evolution can vary by a lot. So there can be very fast flavor evolution and very slow flavor evolution. So how fast or slow these flavor evolution can happen, that depends a lot on the angular distribution with respect to the radial direction of neutrinos. So if we plot the angular distributions of neutrinos, so this again is the angle with respect to the radial direction. So this is the radially outward direction, this is the backward direction, and you have nu e's in red and nu e bars in blue. If there is a crossing like this, if there is a crossing between nu e and nu e bar, then the neutrino oscillation probabilities can evolve really fast. And this is called fast flavor evolution. Even if we don't have this crossing, neutrino oscillations can happen, but then they are slow. So if we try and figure out what is the effect of this, including these oscillations, on the energy spectrum. What we see is something like this. So initially, what was nu E and nu X, they became closer to each other. Okay, so this dashed line is the energy spectrum if we don't include flavor evolution. The solid line is what happens when we include flavor evolution. Now notice what has happened. The tail, the high energy tail of the electron neutrinos, which was very small, it was not big, it got enhanced due to flavor evolution. What that means is that the heating due to electron neutrinos has got enhanced, okay? And same with nu E bars. So what we are finding now is that if we include neutrino flavor evolution in this calculations of core collapse supernovae, the heating becomes far more efficient. And no BSM is required. Normally, the solutions which require BSM can do this. If you add BSM, you can enhance the heating due to neutrinos. But here we are not including any beyond standard model physics. All we are including is the interaction between neutrinos mediated by Z boson. So this is completely within standard model, except for the neutrino masses, of course, but that is given. So when we include the flavor evolution, what we are finding is that it helps with the heating of the neutrino-driven heating. But when we include the enhanced neutrino heating, we are not just including the enhanced neutrino heating, we are also taking into account the fact that the electron fraction is changing due to this change in the physics. And as far as the future of this field is concerned, what we need to do is include a self-consistent formalism of neutrino flavor evolution in core collapse supernova simulations, which has not been done yet. And the same thing needs to be done as far as the R process nucleosynthesis is concerned. And I'm not going to talk about much about it today because Mariam is going to talk about it tomorrow. So that is all I have. And this is the summary. So as far as neutrinos are concerned, we have known for quite a bit of a time that they play a very important role as far as neutrino dynamics, supernova dynamics is concerned. But what was not realized is how important the flavor evolution aspect of it is. And to the extent that nobody has ever bothered including it in hydrodynamical simulations of supernovae, they have just started to attempt such a thing. And hopefully we will have some interesting results in that regard soon. Thank you.
Shashank? Are there questions? Yeah.
Thanks for the nice talk. I was wondering, so when you say we have to include the fully self-consistent neutrino interactions, does that also involve the full coupling with the fluid? Like, is it possible to do the neutrino interaction as well as the self-consistent feedback with the fluid, with underlying fluid, I guess?
It has not been done yet. We don't know whether we can do it, but we are trying.
Okay. But what do you think it will take for us to be able to do that?
Well, it depends. Are we talking about 1D or 3D? 3D, I don't have much hope. 1D, maybe someday, very soon. Yeah.
So this is spherically symmetric 1D.
Yeah, spherical symmetric 1D.
I have a question. When you show the plot with a theta, like maybe this was like the first slide or something, okay, and showing that for large radiuses, we expect that there is like some preference direction. I'm wondering why it's not symmetric, like why it's only one.
Oh, yeah. So basically here, what we have is that this is a sphere, right? So this is radially outward direction. This is radially inward. And we have a sphere and the neutrinos are being emitted. So they are emitted in radially outward direction. They cannot come back.
Okay. Okay. So it's 0. It's like the angle.
So theta equal to 0 is the radially outward direction.
Okay,
So the
okay.
cos theta equal to 1, this is radially outward. This is radially inward.
Okay. Okay.
Yeah.
Other questions? So this relative electron neutrino heating that you showed, what kind of, so you said you cannot solve the 7D equation, but what kind of approximation was using?
Oh, this was using spherical symmetry.
Okay, yeah.
Yeah, but no other approximation. Yeah.
Okay.
Of course, the feedback, the feedback on matter is not included.
Yeah,
but,
that is
yeah. Yeah.
So there's these rotating cores where the MHD instabilities become somewhat more important. So do you think that this effect would be less prominent if it's MHD driven?
Well, actually, I don't know the answer to that question. That's a very nice question, but unfortunately, I don't know the answer to that question. But I would say okay, so the point is that in the neutrino-driven explosion mechanisms, we have to be very careful about calculating the neutrino heating rates, right? So it is a necessity here. There, it might be important, but it may not be necessary for the explosion to go off, right? Yeah.
Okay, thanks.
Any other questions? If one from Maria.
Yes, a very nice talk. So I have a naive question because I'm not working in this field.
Yeah.
So do you expect to have any differences in the neutrino transport equation in the presence of strong magnetic fields? Because, for example, in pulsars where we have strong magnetic fields, then the Thomson scattering cross-sections are different and electron and photon propagation are modeled differently. So
Yeah, so to the 0th order, no, because neutrinos are not affected by electromagnetic fields, right? I mean, the interaction of neutrinos with the electromagnetic fields is proportional to their mass, so that's very small. But yeah, so that will be a second order effect. Yeah. So I don't think it will be ever that important, especially in the spherically symmetric case where you anyway don't have anything of that sort. Yeah.
Okay, let's thank Shashank again.
Okay.